So this talk's also a little different because we're really going to focus on robots. So I'm going to talk about human-robot collaboration. So we're at a really exciting, this is work done with a lot of human collaboration. This is a picture of my lab, some of the students, not everybody, but some of them, and this work wouldn't have happened without them. So we're at a really exciting time in robotics. Here's the forklift that Andre was talking about. Because we have robots, we just had the DARPA Robotics Challenge this previous week, and if you watch the videos, it really blows you away when you see these gigantic Terminator robots opening doors and driving cars. It's mind-blowing what robots can do today. We have more and more capable robots like this forklift, the IKEA furniture. These U-bots can assemble IKEA furniture autonomously. And as these robots are operating in larger and more complex environments with more and more powerful capability, it's really important that we develop ways for people to interact with them. And that sort of gives the connection between vision and language, because I've really studied ways for people to interact with robots using natural language. This is a picture of the PR2 of my son. So home is another example where these things are good. So this talk is going to be about the work that my group is doing to try to achieve human-robot collaboration in real-world environments. And I'm going to talk about 3 different thrusts that we're working on. The first thrust is really more pure vision. It's about making robots that can carry out actions in real-world environments operating on complex objects. Then when you imagine a robot that can carry out a very large space of possible actions, there's a planning problem that happens, because you get this combinatorial explosion in the space of possible things that a robot can do. So we're going to talk about a little briefly about new algorithms that we're creating that can plan in these very large hierarchical state action spaces. And the reason that we want to be able to do that is, of course, so that they can interact with people. So the last thing I'll talk about is building on these 2 thrusts to interact with people using language. In particular, I'm going to talk about our work incrementally interpreting language so that robots can establish a social feedback loop with their human partner. So this is a picture of my dad's pantry. And it's kind of complicated. There's a lot of stuff in this pantry. And if you imagine a robot operating in a home, this is the kind of task, an environment that it's going to be faced with. What? Lower my volume. I don't know. How's that? Is that better? Okay, this is the kind of environment that it's going to be faced with lots of complex objects, and the person is going to say to the robot out of nowhere, hey, I want the peanut butter, and somewhere in that pantry is the peanut butter, and the robot needs to be able to know what it is and where it is and how to pick it up. So to sort of address this problem, here's another example in our lab where the robot might hand you a tool. If you're cutting an apple, it infers that you need a knife. So it needs to cut the object. So it needs to figure out where the knife, yeah, maybe. Is this scary? This is our lab, not the home yet. All right, so the problem that we need to solve in order to so imagine the robot, you're going to say to something like, hand me the knife, or hand me the peanut butter, or hand me the salt. The robot's got to figure out where that object is in the environment. It's got to figure out where to move its gripper to actually pick it up, and it's got to bring it to the person. So in order to do this, it's really a perception problem. You need to know what the object is. So like this is a simpler environment of the tabletop. This is a ruler. You need to know that it's a ruler because the words ruler need to map to this object that's out there in the environment. You need to know where it is. So here I drew the pixel segmentation that we did automatically on a very easy tabletop environment. But you also have to know where it is in the 3D environment so that you can move your gripper to it and close. And maybe also so you can interpret gestures. If they're pointing and you don't know where it is, you can't interpret those pointing gestures. And then finally, you have to know where you're going to put the gripper. So our robot is a Baxter. It's got a 4-centimeter parallel gripper. The best place to grab this ruler with that robot is in the center. And you need to actually know where on the object, not just where the object is, but where on the object is a good place to grasp it in order to pick up the object and move it somewhere else. I think of pick and place as kind of a platform level thing for a robot to do, a mobile manipulator. The first thing it should be able to do is pick something up and put it down somewhere else. So the approach that, so conventional approaches fall into 2 categories in robotics. The first approach is sort of the dream. It's category-based grasping. I would love to be able to go into my lab, hand my robot an object that I've never seen before, and immediately know what it is, be able to localize it, and be able to pick it up. This is an unsolved problem, at least at the robustness that we need in order to do a lot of the applications that we want, a lot of these cooking applications. If you tried to do that with the objects in my dad's pantry, it wouldn't work. So a lot of people in robotics take an instance-based approach. So the idea is that you say, okay, I'm not going to do category for now. We'll let CVPR solve that problem for us someday. And instead, we're going to say, we're going to limit ourselves to these 10 objects. We're going to collect lots and lots of data about these objects. People collect point clouds, they collect images, they make meshes of this data. There's a project at Berkeley called Big Bird where they have a scanning table where you can scan an object to make these very detailed models. And it works. It works really well because you get to cheat. You get to trust on your training set. So you can very accurately localize an object if you've already seen lots and lots and lots of pictures of that exact object. So our approach is sort of trying to get the best of both worlds. And what we're doing is we're taking an instance-based approach to detection and manipulation, but instead of having a person collect that data with a special setup, we're collecting that data with the robot automatically. So the idea is you come into my lab and you hand the robot an object that it's never seen before. We can't pick it up right away, but if you give our robot, not us, but our robot, 15 minutes to collect this data, at the end of that time, in fact, we can, for many objects, localize it, detect it, and pick it up, at least in tabletop settings. So what this looks like, we wanted to use stock Baxter, and I'll say why in a minute. So this is a silly IR scan to turn the arm into a 1-pixel Connect. We don't have a Connect on the hand. It's got an IR sensor, so we're doing a raster scan to get a point cloud. It would be great to do it with a point cloud, but stock Baxter, okay? So now we're taking RGB images of the object. And now what it's going to do, and this is I'm really excited about Linda's talk, it's going to practice, okay? We're actually going to try to pick stuff up. Give us your best category-based graph proposal system. We're going to try. We'll just go down in order and remember which ones worked and which ones didn't work, and we'll fix it up based on that particular object. Okay, so you see the practicing happening. And at the end of this process, this is what the data looks like. We get these images, we crop them out. We arrange to see the object, so I loved how the babies brought the object right in front of the face. We arrange the same kind of thing. We put it on the table so that we can automatically collect these image crops of the objects. We move our camera around to get lots of different views of that object, several hundred per object. This is the Raster IR Scan. 1 frame of a Connect takes a long time. And then this is the showing after this process happens, we're able to pick up lots of stuff. So this is showing the picking up happening. He's going to shake the object to make sure he's got a good grasp. This works really well on lots of objects. It doesn't work so well on the ruler. So this ruler, it infers a grasp near the end of the object. And it's a pretty heavy ruler, and the shape is kind of weird, this triangular shape. So when he picks it up, he's going to shake, and what's going to happen is it's going to fall out of the robot's gripper. Here he goes. This is to try to simulate like moving the object somewhere else. We give it a nice shake. It pops out. That's a bad place to grab that ruler for this robot with this gripper. And there's other objects that don't work so well. So this salt shaker is a really good example. We use IR to do grasp proposal. The right place to grasp this salt shaker is on the handle, but these are black, so it absorbs the IR light. And instead, there's all these nice reflections here. They look awesome. So he tries to grasp it here and not here because our sensor isn't able to detect. There's lots of reasons why grasps might fail. So what we do is we have this RL algorithm, which I won't go into, based on bandits, where we practice. We try different grasps, and we remember which ones worked and which ones didn't work. And when we do this on the ruler, after training, it learns. So we could do reasoning, and maybe we should do reasoning about the physical dynamics, about how things drop. But anyway, he learns to go in the middle of the ruler and near the center of mass. And so the torques are much smaller, and the robot is successfully able to lift the ruler and move it to another place. So this is sort of this idea that we're cheating. The computer vision is completely standard. It's SIFT and bag of words. We do not do anything fancy. But because we're automatically collecting the data, we're able to get good performance out of these models because we can scale up with lots of data. And that's exactly what we're trying to do right now. So this is showing what we've done in our lab. This is running this on lots and lots of objects. This is 4x4. It's going to go bigger in a second. 9x9. We're getting this on lots of Baxters. So I said this runs on a stock Baxter. Baxter is a robot made by Rethink Robotics right here in Boston. And it costs $30,000. There's about 300 of them in the world, in the research world today. What that means is that everybody in robotics, they at least have a friend with a Baxter. They don't have a Baxter already. And our scanning process, even though it's really silly and uses this 1-pixel connect, it runs on stock Baxter with no extra sensing. We can make this model with point clouds and stuff. So our goal is to scale up this scanning process to collect models of lots and lots and lots of objects. So if we can get all 300 of these Baxters scanning using our existing scan for 11 days, we would have 1 million object models, instance-based object models that are completely specific to the object. But then we would have new tools to attack category, because we'd have data like Linda has, where you can show you have the object, you have multiple different viewpoints, and you have the results of actually manipulating the object. So this is one of the things that we're doing to try to make pick and place work. And before or after learning, we do a lot better because we can fix up the problems. Okay. So then, if you can manipulate lots of objects, the next problem is how can you plan in the resulting really large state action spaces? Even if you just talk about moving objects to other places, picking them up and moving them to other places, there's a combinatorial explosion in the state action space. And we wanted to look at this in simulation. So the simulator that we're using is a game called Minecraft. Who's heard of Minecraft? Lots of people. Yeah, okay. Some people. Who's played? Fewer people. Interesting. It's a really fun game, I will say. And it really captures this idea of like pick and place in Block's world. There's also like zombies and stuff. There's this large, insanely large hierarchical state action space. And this is showing one of the problems that we've been studying, where it's a grid world, which is studied a lot in reinforcement learning. But it's a grid world where this agent has 2 different blocks that he can put anywhere in the environment. And the goal is to go from here to here. So, and then there's a trench. So what should he do? Fill in the trench. Yeah, he should make some kind of bridge, right, a bridge across the trench. And most Minecraft players wouldn't even think about it. They would just go and do it immediately. If you encode this as like an MDP in a naive way, the agent will spend a ton of time exploring actions. The state space is huge. Exploring really stupid actions, like what if I played this block here and this block here? Does that help me? I guess not. And then all the possible combinations of all the possible blocks. It gets even worse if you imagine what people really do in Minecraft, like building houses or castles or tunnels or farms. Minecraft is actually, it's Turing complete. People have made computers in them, graphing calculators and stuff. If we could do all of Minecraft, we could do all of AI, I think. Well, if you can, I think it's true though. All right, so the problem is how can we plan in these really large state spaces, which is by analogy the same kind of thing that a robot faces. So our approach, where really what you want to do is make this bridge. So our approach is to learn knowledge about how to prune the state action space by sampling problems and solving small problems and then generalizing that knowledge to large problems. And the knowledge that we call it affordances, although my students have rebelled and they said, no, it's not really affordances. We also call them goal-based action priors. And the idea is that you learn that if you're trying to get somewhere and you can walk everywhere around you, it's a bad idea to place blocks. But if you're trying to get somewhere and there's a trench in front of you, then maybe it's a better idea to place blocks. It's soft information about a policy. It's not a policy, this is what action I should take at this state. It's just guidelines or heuristics that guide the searching process. So it's still searching, so it can adapt to new and different environments that it hasn't seen at training. But it's able to do it much more quickly than otherwise. Where we've gotten to with this work, one of the reasons I went to Minecraft is I didn't want to have to solve computer vision to do interesting problems. And it's true because you can get out the state of the world programmatically. You can find out where all of these blocks are. But what we realized as we scaled this up, it's actually not true that you don't need to solve computer vision to do these kinds of problems. So for something like the trench, if my representation of the world, even if I can tell you that these are all grass blocks and these are not and stuff, there's still a perceptual problem I've got to solve to know about this trench, as a trench. And similarly for things like walls and trees and mountains and other things in the environment. So what we realized is that we tried to sort of make perception be solved, that it wasn't actually solved. Even in these simulated environments, there's very interesting perceptual problems that need to be solved to map between vision and language. The final thing is we just actually, earlier this week, we announced the release of BurlapCraf. So Burlap is Michael Littman's reinforcement learning and planning framework. It's a mod for Minecraft that runs Burlap inside of Minecraft. So you can run A-star and Rmax and everything else, but it's a huge library that's got all kinds of RL algorithms inside of the actual Minecraft virtual machine and do whatever you want. So Atari, if you're in RL, you maybe heard of the deep-blind Atari thing. We have algorithms that can play Pong and stuff. This is next. Minecraft, right? So it's a much harder and much richer space than the Atari games. And we think this should be one of the next challenge problems for RL. Okay, how much time do I have? Great, okay. All right, so this is, so that thread is about planning in really large state action spaces. The final thing, and this is sort of circling back around to natural language understanding, is interpreting what people are saying. And I've talked before about the symbol grounding problem, mapping between words and language and stuff that's out there in the environment. And it's really hard because people use lots of different natural language commands for describing actions in the environment. The problem, and I've done, this is some of the work that I've done in this area, the forklift up there, the ground vehicle at Olin, the PR2, and up here is the helicopter. And all of these systems, this person saying something, the robot is thinking, and then the robot is going off and doing something. And there's been a lot of other work as well in solving these types of problems. But if you watch these videos, there's a problem in all of them. And the problem is that after the person stops talking, there's a really long delay before anything at all happens on the robot. All of these systems are operating in what I've been calling batch mode. You say something, the robot thinks. And at the point where it's thought, even for 10 or 20 seconds, the person has already decided the robot's broken if they're not us, right? Because it hasn't responded. Even if it goes on to do the right thing, the interaction, the experience of this is quite disconcerting because it seems like it's just ignoring you. And if it goes and does the wrong thing, that's even worse because you waited and you didn't even get it to do what you wanted it to do. So instead, what we're trying to think about is making robots that can close this feedback loop with the person. So instead of doing it batch mode, we want to do it online. We want to interpret what they're saying and what they're doing at a much higher frequency so that we can close the feedback loop. Yeah, skip so I don't run out of time. So humans do this a lot. So social feedback is happening all the time in human-human communication. Herb Clark has a study where one human is instructing another human to assemble objects, and they're 2 times slower if they can't see the same workspace. If you give the human a recorded set of instructions, even if they can stop and play back the recording so that there's like not timing effects, they make 8 times as many errors as if they were able to talk to each other and ask questions and have this kind of feedback loop. And yet our robots aren't really doing this at all. And our robots are faced with a much more challenging problem than the human-human problem because their sensing is nowhere near as good as what the human sensing is. And the mental model that the human has of the robot is who knows what it is and how it relates to the reality of what the robot actually sees. So there's an even greater need for it, and yet we're not doing it. So what we're doing now in my lab is making models for incremental interpretation of language and gesture, where we update the model at a very high frequency based on our observations of the person. So mathematically, it's really simple. It's a generative model. It's a Bayes filter, or an HMM. It's a lot like what LP thinks about. So there's the hidden state, which is what's in the person's brain. And there's observations, which are conditionally independent given the state. So this is the language and the gesture at each time step. And then there might be contextual information that controls how the state evolves over time. So in our model right now, the hidden state is just which object. We're assuming we're only fetching objects, and there's some Markov process over which object that you want. I'm going to give you this one, and then I'm going to wait and think and watch, and then I'm going to give you the next one, and then wait and think and watch, and give you the next one. So the thing that's interesting about this is that we're able to update this model incrementally in real time at a much higher frequency than any of these batch models. So we are doing a model update at 14 hertz right now with our system, as fast as we get new information from gesture. And every time we get a new return, we don't wait for the whole sentence from the speech recognition. Every time we get a new word from the speech recognition system, we do a model update and update the robot's distribution. So the best way to see this is a video. So here he's pointing, and you're seeing the probability of a particular object up in this bar graph. And I'll play it again, but like it's going to be animating. Every time the frame goes in the animation, that's actually a model update that happened based on his gestures. The true state, assuming, is one of these 4 objects, 2 spoons and 2 bowls. So there's 4 bars up there. And as he points and talks, you're going to see this belief state evolve over time. So I'll play it again. So here he's pointing. And it's going up and down based on our model of how to interpret pointing gestures. And then we'll have language. So he says, I would like a bowl. And you see both of these 2 bowls jumped up as soon as it got the bowl observation. And then he points, and that's ambiguous, right? There's 2 bowls. And then he points, and the model is disambiguating language and gesture. Here it is again. I would like a bowl. Then he points to the metal bowl. It disambiguates language and gesture. We also get a kind of compositional semantics out of this just by incorporating the timing information. So here he says, I would like a spoon. That's ambiguous. It's both of the spoons go up. Then he says, the plastic one. That's also ambiguous. There's 2 plastic things. There's a plastic spoon and a plastic bowl. Even though each of those, this is a unigram language model, even though each of those utterances on their own are ambiguous, because we're incorporating this timing information, we're able to combine information from across those 2 utterances to disambiguate what the person is saying. So this timing information is very important. Then that's the other direction. So if he's going to deliberately make an ambiguous gesture, and then disambiguate with language, which is also itself ambiguous, and show that we can interpret that. So why is this important for a robot? So what we're going to be showing here is one of our very first iterations of making a robot produce social feedback. So people produce social feedback by like nodding and looking and pointing and asking questions. Here we have this face, it just flips between confused and not confused, and hard-coded animated gestures. The advantage of a model like this one that updates so quickly is that the robot knows what it knows, and it knows it fast. When it's confused, it immediately knows it is confused. As soon as it gets words or gestures that unconfuse it, that model updates, and it knows. And that's an opportunity for the robot to produce feedback to the person, to close that feedback loop and reduce the errors in the interaction. And this is showing, like I said, the first version of this. In my lab right now, this is like our goal. Like we're exploring all kinds. We have collaborators with RISD to make better faces for us. We're exploring different looking behaviors and different pointing behaviors to try to increase the speed and the accuracy of human-robot interaction in terms of object fetching by producing this feedback. So I'll show you quantitative results. So if we randomly pick an object and there's 4 objects, 25%. Language only, we get 46%. This is actually lower than you'd expect from speech. This is not just speech recognition error. This is because people are pointing and saying that one. And if you correctly recognize that one, and you still can't tell from just the words what it is. So that's why language is so low. Gesture is 80%. If you combine language and gesture, this is with people who aren't us doing this task. If you combine language and gesture, we do even better. So we're actually successfully getting complementary information from language and gesture. So what we're doing right now, this is with just 4 objects. We're scaling this up to more objects, and we're making the task harder. And this is our baseline. And there's going to be more columns, hopefully by the end of summer, with other conditions where we're turning on different kinds of social feedback to try to see how much we can improve the accuracy as the task gets harder when the robot's able to express what it knows and what it doesn't know. This is one of our newer faces. So it's animating. So again, the bar graph is animating. Now there's a face. Actually, if you come in my lab now, it's down in Providence, an hour south of here. You'll see a face animating smoothly based on the entropy of the underlying distribution. So there's like cool animation and there's cool math at the same time, which makes me really happy. Okay, so that was my talk. I talked about making robots that can robustly perform actions in real-world environments. That's that big scanning project. So if you have a Baxter and you want to donate time, come talk to me. And then robots that carry out complex sequences of actions in the real world. This is not in the real world, actually, this is Minecraft. Complex sequences of actions in very large state action spaces. And then finally, robots that actively coordinate with people, establishing a social feedback loop. Thanks.